So today we're going to be doing basically three calculations using our circles, but these are going to be very familiar concepts because we're going to come back and look at some formulas that we know and are comfortable with and see how we can now apply them to deal with concepts that we call sector area, arc length, and then by extension, segment area. So let's start with arc length. So when we're thinking about an arc, remember an arc is something like this. If we have y here, z there, and we have the distance between y and z, right? If we just highlight that, that's an arc. We had what we called an arc measure, which referred to the angle measure, right? The degree measure, but the length now is talking about distance, right? If I ask you for a length of string, you're not going to give me 3 degrees of string, right? You're going to give me like 3 inches of string. So when we're looking at arc length, we're basically looking at a small part of the circumference. Okay, so if we call this circle C, and we're looking for this arc length, which remember is part of the circumference, how do we just calculate that? Well, we know circumference is 2 pi times radius, right? So we know that that radius is going to be an important measurement, but we don't want the whole thing because we don't want to do the whole circle. We just want the distance from y to z. So what else do we need to know? Well, we do need to know that arc measure, right? So we want the arc measure of the arc length we're trying to find. And that tells you what part of the circle, right? Is that 30 degrees of the whole 360? Is that 175 of the whole 360? It tells us what part of the pie we want. So our arc length formula is simply 2 pi times radius times m over 360 degrees. And that's because, right, we don't want the whole circle. We want a piece of it. What piece do we want? M over 360, right? Because if we're looking at 90 degrees, we want a quarter circle. So that tells us that. So this is hopefully very familiar because you're like, wait, 2 pi r, I know that. Now we just need to multiply by the piece of the circle. So if we look at example 1 and pretend that I already have this written in, this is circle A, and we're looking for the length of arc BC, which is from here to here. And this has a measure of 112 degrees. Our radius is 4 inches. So that's all part of the problem. And we want to round our answer to the nearest hundredth. Let's go ahead and calculate that. So go ahead and plug it in, and let's see what we get. So as long as we know R and M, it's pretty straightforward. You just plug it all in. Right? Remember, it's always a good habit to write down the formula. So 2 pi r times m over 360. We know r is 4, m is 112. Plug it all in. I showed you the simplified fraction in case it asked you to leave your answer in terms of pi, but because we're rounding to the nearest hundredth, put it all in your calculator, use that pi button. We should get 7.82. Okay? So that is arc length. Now, sector area is a very similar thing, but the difference is, of course, we're not looking for length, we're looking for area. So let's first talk about, well, what is a sector? So if we have a circle, let's call this circle B. A sector of it is a full kind of slice of the pie. So if we look at this arc A to C, we can create a sector by basically connecting these two radii, BA and BC, and kind of making this Pac-Man image. So this shaded region is a sector. So sector area is just a part of the overall area of the circle. So it's part of the area. It has to go to the center. Think about like a slice of pie. All right, so we're cutting from the center all the way out to the edge of that circle. So then very similarly, we're like, wait, I don't want the whole area. I just want a part of it. And I'm thinking, wait, it has to go to the center. So this central angle, right, matches the arc measure M. So that tells me what part of the circle I want, 50 degrees, 85 degrees, whatever. So I can just multiply my area formula by the piece of the circle I want. So sector area is pi times radius squared times m over 360, because again, it's just a slice of the circle that we want, right? So it's a part of that pi r squared. What part do we want? M out of 360, which tells us how much of the circle we're doing, okay? And that's why it does have to, the sector area does have to hit the center, okay? So if we look at example 2, let's go ahead and pretend this is all written in. This is circle G, and we have this arc HJ that measures 30 degrees, and we have a radius of 5 feet. We're looking for the area of this sector, and we want to leave our answer in terms of pi this time. So what are we going to do? Okay, well, start with your formula. And just like with arc length, plug it all in. But we want to remember to reduce this, so we want to simplify in terms of pi. So go ahead and substitute it in and try working with your fractions, and we'll come back and check our answers. So just remember to simplify a little bit at a time. 5 squared is 25, 30 over 360, you can cancel out the zeros, right? Cross out those zeros. 3 over 36 is 1/12. 25 over 12 doesn't simplify any further, so we have 25 over 12 pi square feet. Now if it asks you to round, go ahead and put that in your calculator. Again, use your pi button. Okay, then we've got one last bit to go over, which is segment area. Okay, so now let's talk about segment area. So the first thing we need to do is first understand what is a segment. So we've talked about sector area, which remember is basically a piece of a pie. So if we call this circle C, we can then cut a piece out of this, right, and create the sector. So we talked about this before. This is a sector, but this is not a segment. So what is a segment? Well, segment is actually just a little sliver of your circle. So for example, if I have 2 points A and B here, I can create a chord. So the segment is now the little piece of the circle between the chord and its corresponding arc. So this is our segment area. So you can see how it's very different from sector area in that it doesn't go all the way to the center. It's just this little tiny sliver on the side. So it's the area between a chord and its corresponding arc. All right, so once again, segment area is the area between a chord and its corresponding arc, but we still name the segment based on kind of the corresponding sector, but we'll just write the word segment instead. So for example, oops, pointing at the wrong thing here. So for example, this segment is what we'll call segment ACB. So we'll name it based on the sector, but we'll write the word segment in front so we know it's just that little sliver. So now we have to think, okay, great, now we know a segment, but how the heck do we find the area for this? Because it's not like a specific slice of the circle, it doesn't go all the way to the center. Well, here's where we have to combine the idea of sector area and composite shapes. So what I want you to do is think about, wait, how do we actually create a segment? So if you think about this, we basically take a sector, right? So this is sector ACB. So we start with this. And we don't want the whole thing, right? So we want to take away a piece of that sector to leave behind just the segment. And if you think about it, what shape do we take away? Well, I'm taking away this triangle. So what we're basically going to do is there's no formula for this. It's just a plan. We're going to find sector area and take away the area of the triangle using these radii to help us get the area of that triangle. All right. So again, segment area equals sector area minus area of the corresponding triangle, which remember we want to use that radius to help us out with that. So example 3, this last one, sorry, I forgot to put in these numbers, but we'll call this circle M, and we're looking for the area of segment LMN. We want to leave our answer in terms of pi, and this is information that is in the problem. So each radius is 9 inches, and the central angle is 120 degrees. Okay, so our segment is this little piece right here. So if we think back to, okay, segment area, it's telling me segment, I've got my plan, I want to do sector area minus area of the triangle. So my sector, remember, is that formula we just talked about. This is pi times radius squared times m over 360, right? Whatever piece of the pie that we want. So here we know radius is 9, so that's pi times 9 squared. M, the measure of the arc, is the same as the central angle, 120 over 360. So that's pretty straightforward, and we can simplify that, right? So that's going to give me pi times 81, and this reduces down to 1/3. 1/3 of 81 happens to be 27 pi. Beautiful. So now we have our second piece. We want to figure out the area of this triangle. So how do I figure out the area of the triangle? Well, if it helps, feel free to redraw it. And I'm going to look at this triangle, but not just say, okay, I only know this is 9 inches. Remember, each of these distances, m to l and m to n, are radii. And what do we know about all radii in a circle? Well, we know they're all congruent. So what's neat is this is always going to be an isosceles triangle. All right? And remember, to find the area of a triangle, we know this is 1/2 base times height. So we want to go straight across to make a right angle. Then we have B, then we have H. And why am I doing it this way? Well, if you think back to our unit on properties of triangles, when we talked about the perpendicular bisector theorem and all that, this is helpful because if we have this height, which is perpendicular to the base, since each radii are the same, this height will also bisect the base, which then allows us to work with a right triangle, which has been a foundation to a lot of what we're doing. So again, I'm just kind of rotating this. This is the height. This hypotenuse is my 9 inches. And this is 1/2 of B, which I'll call X. That's 1/2 of my base for me to remember. So what are we going to do with this? Well, obviously, if I only have one length, I can't do my Pythagorean theorem. So I want to think about, wait a minute, I've got a central angle measure. So remember, this central angle is 120 degrees. So if I can divide that by 2 to get that top angle of my right triangle. And now that I have a single angle measure, I can do Sohcahtoa, I can do potentially special right triangles depending on what I have. And this happens to be a special right triangle because it's 60. Does it always have to be a special right triangle? The answer is no. So actually, I'm going to rewrite this, and let's go ahead and round this to the nearest 10th. Sorry, that's really messy, but that says round to the nearest 10th, because I want you guys to see that it doesn't always have to be a special right triangle. So how do we do this if we don't really care about getting an exact value? Well, we can do Sohcahtoa, right? So if I'm looking for H is the adjacent, 9 is the hypotenuse. Adjacent over hypotenuse is cosine. Cosine of 60 is H over 9. I can multiply both sides by 9 to get 9 times cosine 60 equals the height. X, which is half of my base, opposite, and I know 9 is still the hypotenuse, opposite over hypotenuse is sine. Multiply both sides by 9. That's my X, and then I know B is twice that, so 18 times sine 60 is my base. So then the area of this triangle is 1/2 of 18 sine 60 times 9 cosine 60. All right. And we can clean that up a little bit, and we can do half of 18, which is 9. 9 times 9 is 81. So 81 times sine 60 times cosine 60 is the area of that triangle. And remember, our end goal is the segment area, and we always like to round just once. So if your calculator can do it, go ahead and put this whole thing into your calculator. If not, do it one piece at a time, right? You can do 27 times pi. Use that pi button in your calculator, and then write down what you get from there. Then you can find 81 times sine 60 times cosine 60, write down what you get from there, and then Subtract, and we should get approximately 49.7 square inches. Okay, so I think the trickiest part to this is really just finding the area of the triangle. But if you remember, we're always going to do Sohcahtoa. We will always know our radius. So we're going to do sine and cosine. Cosine to find the height, sine to find half the base. And if you just remember that process, keep practicing it. The only thing that changes is the length of the radius and the measure of that angle. All right, so that is segment area. Please let me know if you have any questions.